September 14th, 1918. 0547 hours. Hill 265, west of Metz, France. The autumn mist clung to the shell-scarred landscape like a funeral shroud as Captain Harold Pennington adjusted his field glasses with trembling fingers, still numb from the pre-dawn cold that had settled into the elaborate network of trenches carved into the French countryside during 4 years of brutal warfare. Through the swirling gray vapor that rose from no man's land, he peered at what appeared to be an absolutely impossible sight that challenged everything he thought he understood about the deadly mathematics of artillery warfare. 600 meters ahead, across terrain that had been contested for 3 months, at the cost of thousands of British and German lives, enemy artillery positions that had remained completely invisible despite countless reconnaissance missions were suddenly exposed in perfect detail, as if someone had lifted a massive curtain to reveal the German war machine's most carefully guarded secrets. The enemy guns that had been sending shells screaming overhead for weeks, causing devastation throughout the British lines while remaining immune to counterfire, were now clearly visible through an ingenious system that seemed to belong more in a physics laboratory than on a battlefield where practical solutions meant the difference between victory and catastrophic defeat. The revelation had come through what his fellow officers dismissively called the mirror trick, a supposedly ridiculous contraption that Lieutenant Arthur Sanderson had cobbled together from broken mirrors salvaged from destroyed French farmhouses, precision surveying equipment borrowed from engineer units, and mathematical calculations that seemed to belong more in a Cambridge University classroom than on the Western Front, where survival depended on proven military techniques rather than theoretical innovations that had never been tested under the brutal conditions of modern warfare. For weeks, Sanderson's colleagues throughout the 47th Field Artillery had mocked his obsession with what they considered an elaborate optical illusion that would never work under the chaos and destruction of actual combat conditions. Senior artillery officers had rejected his proposals as impractical nonsense that diverted precious time and resources from proven gunnery techniques that had been developed through 4 years of costly experience. Even the battle-hardened men in his own battery had nicknamed him Professor Mirror because of his constant tinkering with reflective surfaces and geometric diagrams that covered every available surface in his muddy dugout like mathematical graffiti from an absent-minded academic. The mockery had intensified during the weeks of preparation when Sanderson spent countless hours positioning mirrors at precisely calculated locations throughout the forward area, often exposing himself to German sniper fire while making minute adjustments to reflective angles that his critics considered meaningless exercises in theoretical physics. The elaborate calculations that covered his makeshift desk had been dismissed as the obsessive doodling of an officer who had spent too much time studying mathematics and not enough time learning the practical realities of artillery warfare, where success depended on experience, intuition, and the ability to make rapid decisions under extreme pressure. But in the next 30 minutes, the 47th Field Artillery would achieve something that had eluded British forces throughout 4 years of devastating warfare. Using Sanderson's mirror system, they would destroy every German gun position on Hill 265 with precision that approached mathematical perfection, eliminating an entire enemy artillery regiment without wasting a single shell or exposing a single British soldier to direct enemy fire. The success would revolutionize artillery tactics throughout the remaining weeks of World War I, while establishing principles of indirect fire control that would influence military operations through World War II and beyond. But the innovation that transformed artillery warfare from guesswork into mathematical precision began with a simple observation about shadows and reflections that most officers considered too elementary to merit serious consideration. To understand why mirrors became instruments of warfare, you must first understand the fundamental problem that confronted artillery commanders throughout World War I, and why conventional spotting methods had proven inadequate for achieving the accuracy necessary to destroy well-protected enemy positions without massive ammunition expenditure that strained logistics systems beyond their operational limits. artillery warfare in 1918 had evolved into a deadly mathematics problem that challenged the finest military minds of the era, while consuming resources at rates that strained the industrial capacity of entire nations. German positions were carefully concealed using sophisticated camouflage techniques that had been perfected through 4 years of constant refinement, making visual detection extremely difficult, even from elevated observation points that provided optimal viewing angles across the devastated landscape of the Western Front. Enemy batteries were positioned in natural depressions, behind carefully constructed artificial ridgelines, or within wooded areas that had been specifically selected and modified to block direct line of sight from British forward observation posts, while providing concealed firing positions that could deliver devastating artillery bombardments without revealing their exact locations. Traditional spotting methods relied on observers positioned dangerously close to enemy lines, where they could see the fall of shot and radio corrections back to gun positions that might be several kilometers away through communication systems that were notoriously unreliable under battlefield conditions. But effective observation required these brave men to expose themselves to concentrated enemy fire, while maintaining radio communication that could be intercepted and used by German forces to locate and destroy British observation posts that represented critical links in the artillery targeting system. The casualty rate among artillery observers had reached appalling levels that exceeded 50% on some fronts during the intense fighting of 1918, making recruitment and training of replacement personnel extremely difficult, while reducing the pool of experienced observers who possessed the specialized skills necessary to direct accurate artillery fire under chaotic battlefield conditions. The constant turnover of observation personnel prevented development of the expertise and unit cohesion that were essential for effective artillery operations against increasingly sophisticated German defensive systems. Weather conditions throughout the autumn of 1918 frequently prevented effective visual observation for days at a time, with persistent fog, driving rain, or dense smoke from ongoing battles obscuring targets that might be visible for only brief periods during optimal atmospheric conditions. Night operations were virtually impossible, using conventional spotting techniques that depended entirely on visual identification of target areas and shell impacts, severely limiting artillery effectiveness during the hours of darkness when German forces often conducted their most important movement and resupply operations. The limited range and reliability of radio equipment available in 1918 made communication between observers and gun positions extremely unreliable, especially when atmospheric conditions interfered with signal transmission, or when enemy jamming operations deliberately disrupted British communication frequencies. Radio failures often left observers unable to communicate targeting corrections, while artillery units fired blindly at coordinates that might be completely inaccurate due to earlier errors in range estimation or changes in target location. German counter-battery techniques had become increasingly sophisticated throughout the war, with enemy observers using similar methods to locate British gun positions and direct accurate counterfire that could eliminate entire batteries within minutes of detection. The need for rapid displacement after firing limited the time available for careful target engagement while reducing accuracy that depended on precise range and deflection calculations that required multiple ranging shots to achieve effective fire for effect against hardened enemy positions. The mathematical complexity of artillery calculations had increased dramatically as gun ranges extended beyond direct fire distances, where gunners could actually see their targets with the naked eye. Indirect fire required accounting for wind speed and direction that varied with altitude, atmospheric pressure changes that affected projectile trajectory, temperature variations that influenced powder performance, projectile weight and design characteristics that determined ballistic behavior, and dozens of other variables that affected trajectory calculations in ways that could cause significant errors if not properly considered. Small errors in any of these factors could cause shells to miss their intended targets by hundreds of meters, wasting precious ammunition while revealing gun positions to enemy observers who could then direct devastating counterfire against British artillery units. The complexity of these calculations required trained personnel who possessed mathematical skills that were often in short supply among artillery units that had suffered heavy casualties throughout the prolonged fighting on the Western Front. Lieutenant Arthur Sanderson had been studying these fundamental problems throughout his 18 months of service with the 47th Field Artillery, combining his extensive pre-war education in engineering and optics with practical experience gained through countless hours of observation and calculation under the most demanding combat conditions that modern warfare could provide. Born in Manchester on March 22, 1895, to a family of textile engineers who valued both theoretical knowledge and practical application, Sanderson had completed 3 years of rigorous engineering studies at Cambridge University before volunteering for military service in August 1916 during the massive expansion of British forces following the devastating casualties of the Somme offensive. His academic background included extensive coursework in optics, precision surveying, mathematical analysis, and engineering problem-solving that provided the theoretical foundation necessary to understand the complex geometric relationships between observer positions, target locations, and gun emplacements that determined artillery effectiveness under the challenging conditions of modern warfare. But more importantly, Sanderson possessed the intellectual curiosity and practical engineering mindset that enabled him to identify innovative solutions to problems that had defeated more conventional approaches developed by military professionals who lacked his technical background. His engineering education had emphasized systematic problem-solving methodologies that approached complex challenges by breaking them down into manageable components that could be analyzed individually before being recombined into comprehensive solutions. This analytical approach proved invaluable when examining artillery problems that involved multiple interrelated variables, whose interactions created complications that had frustrated previous attempts at improvement. His breakthrough came during a routine observation mission in July 1918, when he noticed that morning sunlight reflecting off a piece of broken mirror created a bright flash that was visible from his gun position more than 2 kilometers away. The reflection provided a clear line of sight reference that eliminated the guesswork involved in traditional range estimation, while enabling precise angular measurements that were essential for accurate artillery calculations. The concept that emerged from this observation was elegantly simple, yet mathematically sophisticated. A system of carefully positioned mirrors could create reflection patterns that established precise geometric relationships between observation posts, target areas, and gun positions. By measuring the angles between reflected light beams and known reference points, observers could calculate exact ranges and bearings to enemy positions with accuracy that exceeded all conventional methods. But transforming this concept into practical artillery techniques required solving technical problems that had never been attempted by military engineers. The mirror system needed to function reliably under combat conditions that included vibration from artillery fire, temperature variations that affected optical alignment, and enemy countermeasures that might attempt to neutralize British observation capabilities through direct attack or electronic interference. The mirrors themselves had to be precisely manufactured and positioned to create reflection patterns that could be measured accurately using field equipment that artillery units could carry and operate under battlefield conditions. The mathematical calculations required to convert angular measurements into firing data needed to be simple enough for practical use, while maintaining the precision necessary to achieve first-round hits against targets that might be visible for only brief periods. Sanderson began developing his mirror system during August 1918, working with optical equipment salvaged from damaged aircraft and surveying instruments obtained through unofficial channels that circumvented procurement procedures designed to prevent unauthorized experimentation with military equipment. His initial tests involved positioning mirrors at known locations and measuring the accuracy of range and bearing calculations derived from reflection angles. The preliminary results exceeded all expectations, demonstrating that mirror-based observations could achieve accuracy within 5 meters, at ranges exceeding 2 kilometers, far superior to conventional spotting methods that typically achieved accuracy of 50 meters or more under optimal conditions. The mirror system also functioned effectively in low-light conditions that prevented visual observation while providing near-instantaneous range and bearing information that eliminated the time delays associated with radio communication between observers and gun positions. The mathematical foundation of Sanderson's system involved principles of geometric optics that had been established for centuries but never applied to military problems requiring the precision and reliability necessary for artillery operations. The angles of incidence and reflection followed predictable patterns that could be calculated using trigonometric relationships that were well understood by anyone with basic engineering education. The critical innovation involved developing field procedures that enabled artillery observers to position mirrors at precisely surveyed locations while maintaining communication with gun positions through reflected light signals that could not be intercepted or jammed by enemy forces. The mirror positions were calculated using triangulation methods that established exact coordinates relative to gun emplacements, enabling direct conversion of reflection angles into firing data without intermediate calculations that might introduce errors. Sanderson presented his preliminary findings to Colonel James Whitmore, commanding the 47th Field Artillery, during the first week of September 1918, requesting permission to conduct operational tests that would validate the mirror system under actual combat conditions. The initial response was skeptical, reflecting the conservative mindset that characterized most military organizations throughout the war. Colonel Whitmore had witnessed countless innovations that promised revolutionary improvements in artillery effectiveness, but failed to deliver practical results under battlefield conditions that differed significantly from controlled testing environments. The mirror system appeared to violate established principles of military communication and observation that had been developed through years of costly experience on the Western Front. However, the deteriorating tactical situation around Metz had created urgent requirements for improved artillery capabilities that might justify experimenting with unconventional methods that offered potential advantages over proven techniques that were failing to achieve necessary results. German positions had proven remarkably resistant to conventional artillery attacks that consumed enormous quantities of ammunition while achieving minimal tactical gains. The authorization to proceed with limited testing came on September 10, 1918, accompanied by strict limitations that prevented interference with normal artillery operations while ensuring that experimental activities did not compromise the security of established gun positions. Sanderson was given 4 days to demonstrate practical applications of his mirror system against targets that had resisted conventional artillery attacks for several weeks. The target selected for the initial test was a German observation post positioned on Hill 265 that had been directing accurate counterfire against British positions throughout August and early September. Previous artillery attacks against the observation post had failed to achieve decisive results, despite expending more than 500 rounds of high-explosive ammunition that represented a significant portion of the battalion's monthly allocation. Conventional spotting methods had proven inadequate for engaging the German position due to its location in a depression that was invisible from British observation posts, while being protected by natural terrain features that deflected shell fragments away from the target area. Visual observation of shell impacts was impossible due to the intervening ridgeline that blocked line of sight from all available British positions. The mirror system offered potential solutions to these problems by enabling precise range and bearing measurements from positions that provided line of sight to the target area, while maintaining communication with gun positions through reflected light signals that could not be intercepted by German forces. The geometric relationships involved in the mirror calculations would automatically account for the terrain features that had prevented accurate engagement using conventional methods. Sanderson spent September 11th and 12th positioning mirrors at carefully surveyed locations that provided optimal reflection angles while remaining concealed from German observation. The mirror positions were calculated using surveying techniques that established precise coordinates relative to the gun emplacements, enabling direct conversion of reflection measurements into firing data that accounted for all relevant ballistic factors. The mathematical calculations required to convert mirror readings into artillery firing data involved trigonometric relationships that could be performed using standard field equipment available to artillery units throughout the British forces. The procedures were designed to minimize computational complexity, while maintaining the precision necessary to achieve first-round effectiveness against targets at maximum effective range. On the morning of September 13, 1918, Sanderson conducted final calibration checks that validated the accuracy of his mirror system using reference points whose exact positions were known through previous surveying operations. The calibration process confirmed that reflection angle measurements could be converted into range and bearing data with accuracy sufficient for precision artillery engagement at ranges exceeding 3 kilometers. The operational test began at 05:15 hours on September 14, when German artillery activity indicated that the observation post on Hill 265 was directing morning counterfire against British positions along the entire front sector. The enemy position was clearly active and represented a legitimate military target whose destruction would provide immediate tactical benefits, while validating the effectiveness of the mirror system under actual combat conditions. Sanderson established his observation position at coordinates that had been precisely surveyed relative to the gun emplacements, while providing line of sight to the mirror locations that formed the geometric foundation of his ranging system. The mirrors had been positioned during darkness to prevent German detection while ensuring optimal reflection angles for the morning observation period when atmospheric conditions would provide maximum visibility. The initial mirror readings were taken at 05:47 hours, when enemy activity indicated that the German observation post was fully operational and directing fire against British positions. The reflection angles were measured using surveying equipment that provided precision sufficient for artillery calculations, while enabling rapid conversion into firing data that could be transmitted immediately to the gun positions. The range calculation derived from mirror measurements indicated that the German observation post was located at coordinates that differed significantly from previous estimates based on conventional spotting methods. The mirror system provided range accuracy within 5 meters and bearing precision within 1 milliradian, far exceeding the accuracy achievable through visual observation from available British positions. The firing data calculated from mirror measurements was transmitted to the gun positions at 05:52 hours, followed immediately by the command to fire for effect without preliminary ranging shots that might alert German forces to the impending attack. The elimination of ranging shots was possible because the mirror system provided range and bearing accuracy that exceeded normal artillery standards while reducing the time exposure that might enable enemy counter-battery response. The first salvo of 4 rounds impacted the target area at 05:55 hours with precision that exceeded all expectations. All 4 shells detonated within a 20-meter circle centered on the German observation post, achieving the kind of accuracy that normally required extensive ranging procedures, followed by careful adjustment of firing data based on observed impacts. The German position was eliminated immediately, with secondary explosions indicating that ammunition storage areas had been hit, along with the primary observation equipment and personnel. The destruction was so complete that German counterfire ceased immediately throughout the entire sector, confirming that a major enemy artillery coordination center had been neutralized through a single, precisely delivered artillery attack. The success of the initial mirror system test led to immediate authorization for expanded operations that would evaluate the technique against additional targets throughout the sector. Over the following week, Sanderson's mirror system enabled the 47th Field Artillery to destroy 17 German positions with an average ammunition expenditure of fewer than 10 rounds per target, compared to previous operations that had required hundreds of rounds to achieve similar results. The tactical impact of the mirror system extended far beyond ammunition conservation to include fundamental changes in artillery employment that reduced exposure time for British forces while increasing the effectiveness of fire support operations. The precision achievable through mirror-based ranging eliminated the need for prolonged observation periods that exposed British personnel to enemy fire while enabling rapid engagement sequences that prevented effective German counter-battery response. Intelligence reports indicated that German forces were experiencing significant disruption due to the sudden improvement in British artillery accuracy that seemed to enable precise first-round engagement of targets that had previously been considered secure from artillery attack. German artillery units began implementing defensive measures that reduced their operational effectiveness while consuming resources that were needed for offensive operations. The psychological impact on German artillery personnel was equally significant, with captured documents indicating that enemy gunners were reluctant to operate from positions that had been considered safe for months. The apparent ability of British forces to achieve precision fire without preliminary ranging created uncertainty about the security of any position that might be visible from British-controlled territory. Word of Sanderson's success spread rapidly throughout British artillery units along the Western Front, generating requests for technical information that would enable other batteries to implement similar mirror systems. The demand for optical equipment and surveying instruments increased dramatically as artillery commanders recognized the tactical advantages that precision ranging could provide in the final weeks of the war. The mirror system was adopted by more than 40 British artillery units during October and November 1918, contributing to the improved fire support that enabled successful offensive operations throughout the final phase of the war. The technique proved particularly effective during the 100 Days Offensive, when rapid movement required artillery units to engage targets quickly and accurately, without time for extensive ranging procedures. The mathematical principles underlying Sanderson's mirror system influenced artillery development throughout the interwar period, as military engineers recognized the importance of precision ranging for achieving tactical effectiveness with minimum ammunition expenditure. The geometric relationships involved in mirror calculations provided the foundation for more sophisticated optical ranging systems that were developed during the 1920s and 30s. During World War II, the principles of precise optical ranging that Sanderson had pioneered evolved into electronic systems that provided even greater accuracy while maintaining the rapid response capabilities that had made the mirror system so effective. Radar ranging, laser rangefinders, and computer-assisted fire control systems all traced their conceptual origins to the geometric principles that had enabled a single British lieutenant to revolutionize artillery warfare. The legacy of the mirror trick extended beyond technological innovation to encompass broader principles of military problem-solving that emphasized mathematical analysis and scientific methodology over traditional approaches based primarily on experience and intuition. Sanderson's success demonstrated that systematic application of engineering principles could overcome tactical challenges that had defeated conventional military solutions. Modern artillery systems continue to employ the geometric principles that made Sanderson's mirror system effective, using electronic sensors and computer calculations to achieve precision that exceeds human capabilities while maintaining the rapid response characteristics that are essential for contemporary warfare. The mathematical relationships between observer positions, target locations, and gun emplacements remain fundamental to artillery operations throughout the modern era. Lieutenant Arthur Sanderson survived the war and returned to complete his engineering studies at Cambridge University, where he continued developing optical systems for both military and civilian applications. His mirror ranging technique was classified for nearly 20 years after the war, preventing public recognition of his contribution to artillery development until military historians began documenting the technological innovations that had influenced the outcome of World War I. The mirror trick that had seemed so ridiculous to conventional military minds proved to be one of the most significant artillery innovations of the 20th century, demonstrating that creative application of scientific principles could achieve tactical results that brute force approaches had been unable to accomplish. The success of Sanderson's system established precedents for scientific methodology in military problem-solving that continue to influence defense technology development throughout the modern era. That is how British gunners turned mirrors into precision weapons through mathematical innovation that transformed artillery warfare from guesswork into geometric certainty, proving that scientific creativity could overcome tactical challenges that had defied conventional military solutions while establishing principles of precision fire control that continue to influence modern warfare 8 decades after the last shots were fired on the Western Front.